emits a reward. And this reward and state are basically observed by the agent to take the next action. So it's a dynamic process, and then there are parallels with dynamic programming. But the idea is that over time, our hope is to have an agent that can maximize the expected reward. And I'll give you like a specific mathematical definition eventually. But these rewards that are emitted at each time step as the agent performs actions on an environment can be summed up over time in a particular manner, and the sum of these rewards ideally should be high. So you can think of this as an agent playing a game within environments and trying to sort of get a high score, right? Typically, some terminology over here. The goal in the reinforcement learning problem is, of course, that the agent should be intelligent, right? It shouldn't just randomly select actions, and it should actually perceive the value of an action and then connect the value to the reward. So the goal is typically in most algorithms is to learn what is called a policy. The policy is also generally depicted as the SPI term, and this SPI generates an action when it has observed a specific state S. And the idea is that we want to learn this SPI such that this cumulative reward from RT is actually maximized. So this reward over time is maximized. Okay. All right. So in practice, the policy pi that I mentioned in the previous slide, there are various ways to actually parameterize it, right? This can be deterministic, it can be stochastic, which means that there's some, given a particular observation of the state, the actions can vary, or it can be deterministic. And since I have this subscript theta over here, which implies that this pi is typically parameterized by some free weights, so free parameters, which can be then learned to again maximize the expected reward. In this study, we parameterize pi as a neural network, but in practice, something to note here is that it could be anything that is a function approximator. So Gaussian processes are typically used. But neural networks are used, in which case, the reinforcement learning is frequently called deep reinforcement learning because it uses deep learning. But another thing to note, these neural networks are typically not as heavy duty as the ones you see in supervised learning applications, where you have like millions or large language models, right? You have millions and millions of parameters, especially for our applications, which require pretty rapid inference because perhaps the action is connected to a physical system. The goal is, as you can see over here, you'll have some states that are observed by this neural network now, and this neural network will predict an action. This action will go to an environment where we want to control this environment, and there are various examples in this talk. So I'll explain what is here in a bit. And through repeated interactions with this environment, which shows up in this expectation. This expectation is over episodes. So the concept of an episode is that one set of interactions over time comprises one episode, and then you take an expectation over multiple episodes. You basically obtain a loss function that must be maximized. So this reward has to be maximized, right? Another terminology over here, which again I'll mention here, but we won't really look at it again, is this concept of a discounted reward. So the idea is that the rewards in the future are discounted by a multiplier, which is typically set to 0.99 or 0.95, which means that while there is a desire to maximize the expected reward, there is also a kind of a incentive to the agent to also make sure that there is a slight emphasis on like in terms of a greedy search, right? So the first action should definitely be a good one, right? So this is the concept of a discounted reward, right? Okay, so and then this thing happens iteratively until you get convergence, in which case you say that the policy is trained and can be deployed in real time without any training. It will just learn how to maximize the reward. Okay. And so recently, this has been becoming very popular for science applications. Of course, RL has applications in robotics and nowadays even in fine tuning of large language models. So many applications. But within scientific computing or even like just generally speaking physics applications, RL maps really well onto control, as I mentioned previously. And so there have been some really seminal work that has been published recently. So, for example, we have examples of flow control, which is very, very common, coming from Professor Ricardo Villanuesa's group. People have been using it for turbulence modeling. So how to basically model subgrid parameterizations of CFD codes. So how to model, models for turbulence in CFD codes from Professor Komotsakos and Andrea Beck's group, and also for basically trying to see how to control how fish may align to swim to minimize or maximize a collector reward, such as reducing drag. So there's lots of very interesting work that's coming out over here. And on our part, in our group, over the last, I would say, 3 to 4 years, we have also looked at reinforcement learning for a few science applications. However, I must mention that we have not been as active as some of the names I mentioned previously. It has very much been, like a side project that we are very curious about, but we've not really gone the whole hog. But we are getting more interested in using this to solve more and more challenging inverse problems. So even in the previous slide, there were various examples of inverse problems. So one example that we actually looked at for the first time in 2021 was the application of using reinforcement learning just for controlling a chaotic system. So what I have over here is, you can just focus on one of these 3 plots. On the left is Laurent 63. You must be very familiar with it, the famous butterfly attractor. When you set certain parameters of the Laurent 63 system, there are 3 system parameters. You set them appropriately, and you get this dissipative dynamical system that has a invariant sort of behavior, which means that the dynamical system in phase space keeps revolving around this attractor. Those are the purple lines over here. But let's say you basically select some parameters which are not ones which give you the right butterfly attractor. You actually get the black behavior over here. So as you integrate Laurent 63, you essentially see that it reaches a fixed point. So it's not chaotic anymore. It basically just becomes a stationary system. But in this particular work, what we did was we used a reinforcement learning algorithm to keep perturbing the Laurent 63 system, even though it had a stationary point. So basically, even though it was not a chaotic system, we forced it to perturbed it continuously so that it would continue to be on the butterfly attractor. And you can see that's how we got the purple lines over here. Whereas if we hadn't applied this intelligent agent, it would basically, it would start somewhere here, but end up with the fixed point where my laser pointer is. Right. So it's an example of, controlling a chaotic system with reinforcement learning. Another example that we looked at was, in some sense, it was, you can say, a discovery of what is already known for several years, but we wanted to see if a reinforcement learning agent can solve an inverse problem where, given experimental data, these are the circles over here, for time average statistics over for a flow over a backward facing step, time and span averaged. Can you identify what the right coefficients of a CFD turbulence model, a RANS model, are, so that you can actually match the experimental data? And as you can see over here, the best result that we obtained from our CFD data actually recovered a performance that was similar to coefficients that are actually implemented in ANSYS and OpenFOAM, for example. So in some sense, it was something that let's say over multiple decades engineers had done in a hand-tuned manner, but here a reinforcement learning agent was able to actually predict this the right coefficients, right? So just an example of how flexible it can be across various applications, right? RL can also be used for meta applications. So, for example, this is a paper that our group published in 2020, so now almost 5 years ago, where reinforcement learning was not used for directly interfacing with a particular application, but was actually used for identifying the right neural network architecture. So in this particular paper, we tried to build an emulator for the sea surface temperature. So we tried to forecast the sea surface temperature across 2-month timescales. And we wanted to use deep learning to do this, which is completely fine. But as you know, it's not easy to optimize for the architecture for a particular application. So over here, in this particular problem. We parameterized the space of neural architectures as a directed acyclic graph, which shows here, which is on the right-hand side. And a reinforcement learning agent was tasked with walking on this graph and making choices, right? So making a choice for the number of LSTM blocks, making a choice for skip connections, and based on a particular set of choices, which is almost like over here, it's not real time, but it's the idea of like walking across the graph, which is a dynamic process. It would get a reward. The reward would come from the performance of this network on our validation data. And then over time, the reinforcement learning agent actually learned how to build better and better neural network architectures, which then gave us a competitive performance for the sea surface temperature problem, right? So an idea of how this can also be used for, say, things like architecture search or hyperparameter optimization for your various problems, right? So very, very flexible, very generic. And then this final sort of review of the work that we are doing in our group is actually work that was done by Sahil, the organizer and the host of today's talk. He interned with me in, what was it, Sahil, 2022 or was it 2023? I forget. 23?
21 summer, I think.
21 summer, yeah. So he did a lot of the work in the summer of 21, but then it took us about a year or so to really bring it to a shape where we could submit it. And in this work, Sahil actually, of course, led the entire thing. But what we were looking at is this problem of this inverse problem of shape optimization to minimize something like a drag, well, maximize the negative of drag, for example, right? And then the shape of an airfoil was basically parameterized by say a series of polynomials, coefficients of polynomials, which could then be tweaked, right, for each CFD simulation. But you'll come across a particular problem in such an application, which is if your episode, if every instance of an episode is interacting with a CFD simulation, right? So it's solving a CFD simulation to get a reward, then you're looking at incomprehensibly large compute costs, right? So this is a big problem in RL and how it might be applied to, say, inverse problems in scientific computing, which have large simulations involved. So this was the problem I provided to Sahil. And I kind of we kind of discussed that maybe we can do some sort of multi-fidelity learning, right? So the idea is, can we train our reinforcement learning on a poor simulation, which is fast, right? So the training and the convergence happens rapidly, and then can we, as it has converged or as it's about to converge, can we actually port it to our correct environment, but then save a lot in terms of optimization costs, right? So the idea over here was porting weights from a pre-trained model. So model pre-trained using something like a potential flow or X-foil, is not really physical, but giving us a close answer before we port it to something like CFD, which over here was RANS. So as you can see over here, we call it control transfer learning. So if we started training this model, on episodes of before this dashed line, it was low fidelity models. So so essentially the cost in this region where my laser pointer is negligible. And then we ported our weights to now the real application where now we're interfacing with a RAND solver. So each call of the solver is costly. We saw rapid convergence, and so we were able to get absolutely negligible costs for training our reinforcement learning model. In comparison, if we were working directly with the high fidelity environment, which is the RANS model from the start, it would take much longer. So we would end up having to run 1,000 CFD simulations just to reach the same optima, right? So an example of the way I try to think about these problems and try to sort of pose questions about what's really left in sort of bringing these reinforcement learning algorithms to the applications that scientific computing folk typically work with, right? And so that brings me to kind of the research question for this particular talk, which is in many of these applications, including all the examples I showed you right before, we finished the training of our particular model, and then we declare victory, right? We write the paper essentially. But let's say we want to be a little more rigorous about how this agent works, particularly when we start looking at, possibilities of generalization, extrapolation. It's not that clear if, a pre-trained agent is going to work right out of the box in a completely new setting, right? Of course, we understand that if there's a completely new setting, it's not going to work. But is there a way to kind of answer this question a little more rigorously? That is the topic of today's talk. And there has been some work in this area. I would say it is a little indirect. It's not a direct response to this research question, but it sort of poses a similar but slightly different question, which is the concept of interpretability. The idea is that if your agent is not merely a neural network, but is actually something that you can visually inspect in the sense of a system of equations, then you as the human can look at the system of equations and kind of hope to set bounds on the performance of your agent. So you can say, okay, if there is an exponential term over here, then of course I need to be careful about what goes into the exponential term because it could cause an explosion, right? So things like that. And so there's work by Steve Branton's group at the University of Washington. It's called SINDI reinforcement learning, and then at Lawrence Livermore with Dr. Landahuela, which is deep symbolic optimization, where the idea is that in the process of training this policy, you don't get a black box, but you get symbolic expressions, right? So we are not going to be following their approach. We're going to be looking at a dynamical systems viewpoint of doing, of trying to understand how our agents are actually performing, because, in many reinforcement learning applications, they do interface with dynamical systems, either in real time for physical systems or pseudo time when they're actually learning, right? And so in that sense, well, what if we, port techniques from, scientific computing, stuff that we've probably learned in an introductory course on linear dynamical systems, and see how, we can kind of understand the way an agent works, in a new setting, hopefully in a priori, right? Okay, so that brings us to our framework today, which is we call it SALSA-RL. We struck upon a nice acronym over here, but the full form is basically stability analysis in the latent space of actions. So it's not a new reinforcement learning algorithm. It is a way to take a pre-trained agent from pretty much any reinforcement learning algorithm and then do a little bit of stability analysis on it, right? So the idea is that any pre-trained agent, when it's being deployed on any system, it basically performs actions over time. So there will be an action under time step t-1. There'll be an action under time step t. What we do is we say that, okay, let us assume that these actions are actually governed by their own dynamical system, so like a dA by dt term, right? And we'll say that instead of modeling the dynamics in the original space of actions, we find the latent space, right? So we use the encoder-decoder type of model. This should be a decoder, apologies. We use an encoder-decoder sort of model where we compress our it doesn't have to be a compression, it's just a mapping. Let me take that back. So we transform to a latent space Z, we evolve the dynamics in the latent space Z, which I'll get into in a bit, and then we decode from the latent space Z at the next time step to get our action at the next time step, right? Now, what happens in this latent step specifically is at its heart, what the contribution of this work is. The idea is that if you assume that the latent state is actually evolved by a linear operation, right? So you have a linear matrix A, which we don't know what it is, but this linear matrix A that acts on Z and then basically gives us, well, over here in the continuous sense, the time derivative, but essentially you can interpret this in the discrete sense to evolve the state in time by one time step. And more importantly, we also say that this latent matrix A is actually predicted by the states itself. So in this approach, we have to learn two sets of weights or two sets of neural networks given an original policy, pre-trained policy. So we sample actions from the pre-trained policy. We learn this encoder-decoder, and we also learn a neural network that maps from the states that you observe to this matrix, this linear matrix, right? Now, what we get out of this is essentially an ability to then bring to bear a lot of these techniques that we can apply for the analysis of linear dynamic systems on this matrix A, right? And I'll go into this in a bit, right? But aside from that, I wanted to impress on you that in this particular approach, we are not really interacting with the system. We are actually taking actions from a pre-trained agent, right? So the agent is already pre-trained. Our goal is not to essentially improve on a pre-trained model, improve an algorithm that was already there. Although we see in a few cases, we actually do get some improvement by doing this post-hoc learning. But it's just to recover the same performance, but get some added information about how the model works, right? Okay, so all right, so then a little more detail about exactly what I was talking about. This idea of encoding our action into latent space Z, and then we of course assume that in all this work we assume that the first step action is always 0. This is just for initializing our dynamical system and our analysis. And for discrete actions, these are the two equations essentially that we are bringing in over here, right? So we're evolving Z by acting through the action of A on the current time step of Z, but at each time step, the A changes. So this is something that is important, and we should kind of keep an eye on it. Our A is a state dependent matrix, so our A is also changing over time, right? It's not if which is what we wanted to do earlier in this study. If we can find an A that is time invariant, then we solve the problem. We can literally do an eigen decomposition of A, and basically we are done, right? We know exactly how our agent is going to behave given an initial condition. But A is not a state independent matrix. So A changes with time. So in that case, the stability analysis that we're doing is only valid in the neighborhood of a particular state S, right? There's value to this, as you'll see, in the following slides. Okay. Is there a question? Sorry. No. Okay. So just an algorithm that details what exactly we're doing over time, right? Encode an initial action. This initial action can be set to 0. Then you basically evolve this using this step, this iterative process at each time step. Okay. All right. So in this particular work, we will be working with pre-trained agents that come from an actor-critic type of formulation. So, but also this approach, like I mentioned, is kind of compatible with any pre-trained policy. So in an actor-critic reinforcement learning algorithm, the actor is essentially the policy. So something that actually looks at a particular state and decides what action to take. And in our case, we pre-train this. Actually, a lot of these are pre-trained and available from literature, from, for example, the gym environment, right, a benchmark environment. We take this, we just sample these again and again, right, for varieties of states, and then generate our training data for training our latent dynamics module, as well as our encoder-decoder architecture. And then what we do is the critic in an actor-critic algorithm, just briefly, it learns something called a value function. So it learns what the long-term sort of expected reward for a particular state action combination is. So we don't throw it away, we keep it, because we need it for actually training our particular weights for both these sets of neural networks. The policy gradient, so the algorithm over here, the actor-critic algorithm that we're using is something called the DDPG algorithm, the deep deterministic policy gradient algorithm. So it's all right if you don't understand what it is, but what I'm trying to show over here is that to compute the training objective for optimizing the weights of the decoder, encoder, or even the weights of the state, so the state dependent matrix prediction, you simply need to retain the critic from the deep deterministic policy gradient algorithm and its gradient with respect to the action. So basically, it's a simple use of chain rule on an existing policy gradient and it's relatively easy to kind of modify your existing codes to do this post hoc learning, right? So one thing I want to mention over here, if it wasn't clear, is that we have two sets of training when we're doing the SALSA-RL approach. The first set of training is just the encoder-decoder learning. So over here, what we are doing is we're just sampling varieties of actions. We assume their IID, which is again it's a wrong assumption, but we assume their IID and just learn a latent space via basically just how you might train an autoencoder. And then the latent evolution in the latent space, we reintroduce the non-IID-ness. So we reintroduce sequence, and then we learn the latent dynamics using this particular gradient, right? So it's a split training approach. Okay, so all right, so let's say we've done this and we are left with essentially this map to the latent space and the evolution in latent space. What do we gain out of this, right? Well, you might have guessed it when I mentioned linear dynamical systems, but once we have a time-dependent matrix A, we can actually perform some stability analysis, so local stability in the vicinity of a particular state A, because A is a function of S. And some of the things that we can look at are, for example, the spectral radius of this term A, which is given by this expression over here. So the maximum absolute value of the maximum eigenvalue. And so over here, so the idea is that when you have in the vicinity of a state, when your spectral radius is less than 1, then you basically, it says you have local stability. What that essentially means is that the action values from t to t plus 1, a sub t to a sub t plus 1, will have a decrease in the norm, right? So you could have like a high dimensional action, right? Multiple dimensions, but the norm of this action vector is actually going to reduce if rho of AT in a particular neighborhood of the state is actually less than 1. So this is nice because you can actually deploy this without taking the action. So without taking the action, you'll know what will happen to the norm, right? So this is quite nice. The other thing you get out of this is you can actually look at the imaginary components of these eigenvalues, and then you can potentially characterize, oscillatory dynamics. So imaginary components, if the imaginary component is 0, then that means that our agent is not going to oscillate. It's going to basically be flat, right? So it'll have the same action throughout going forward. But if you have a non-negative or a non-zero imaginary value, then you're looking at the agent basically oscillating, right? So these are nice analyses you can do without actually having to even deploy your agent in the vicinity of a particular state, right? So yeah, so if the spectral radius is less than equal to 1 and the imaginary values of the eigenvalues are non-zero, which means you have damping of oscillations. If it's greater than 1, well, it's unstable, so the norm of the actions will grow. And if the imaginary values are 0, you'll basically have non-oscillatory but stable locally dynamics, right? So let's look at a couple of examples, right? So can I play this video? Let's see. I'm not sure why I can't play this video. Okay, I can play the next one. Anyway, so let's take a look at an example. So the simplest example is the pendulum, right? So the pendulum, the goal is to observe the angle the pendulum makes with the vertical axis, as I mentioned over here, and then the angular velocity, and essentially prescribe a specific torque so that in this particular example, the pendulum stays upright. Okay, so I have a video in the next slide how this actually works out. So we take a pre-trained model from the DDPG, we apply this SALSA-RL approach, and we essentially deploy this. So what you can see over here is that in the initial phase, while this is pre-trained, right? So the agent is trained already, and we just we initialize a 0 action and we let it run and with a given state. Initially, you will see that the the action value is actually oscillating. So it's basically the pre-trained agent actually tries to control the pendulum and make it upright. And after some time, it realizes it's able to basically hold the pendulum upright. And you can also correlate that with the nature of the spectral radius. The spectral radius is initially, it varies, right? So initially it's non-zero. It can be less than zero, but that just means the action, the convergence hasn't happened. But after a certain amount of time, you can see the spectral radius basically is less than 1 and then held constant, right? As is the imaginary eigenvalue, which means that there is no oscillation either. So one nice feature of this thing is that you can actually do a nice visualization of the trajectory of the actions, or the trajectory of the observed states, and correlate that to the spectral radius. So what I have in the plot over here on the right-hand side, on the y-axis is a particular state theta, a component of the state theta. We hold theta dot constant, right? And we see how let me change that. We don't hold theta dot constant. We just plot theta versus the spectral radius. And what you can see is that in the process of applying our particular control through our reinforcement learning algorithm, our agent actually avoids areas that are, I don't say it, and this will become clear in a bit, but I don't say that it will never go into areas of greater than 1 spectral radius, because this is a local analysis, but it generally tends to avoid regions of high growth of action norms, and it stays actually near the boundary. And I have more empirical evidence for this in further examples, right? So these dashed lines over here are the contour values of 1. So basically in the green regions, you have a higher spectral radius, so locally unstable, but in the blue regions, you have basically locally stable behavior. So, but the nice thing is, during your deployment, you can get some insight as to how the agent might perform in a region that you don't have to go and explore, you see. So you don't have to actually physically set your agent to be at a particular state in this region to know how it will perform, which is a nice thing. It helps you do a little bit of planning also potentially. And this plot just tells you that the eigenvalue is 0, basically. So for the imaginary eigenvalue, which means there are no oscillations, right? All right. So let's say now this video shows you how the control is actually performed. So initially in this gray region, we changed the definition so that there's a certain period where there is no action performed, so the agent is inactive, and then the control starts. So you can see in this region, there is no meaning to the plots in this region on the lower side, because even though there is a certain spectral radius that is computed because you have a certain matrix A, the application of A on the previous action gives a new action, but that new action is not employed actually in this gray region because the control is switched off. But the moment the control is switched on, you can see again the pendulum, after some initial transients, basically comes to a spectral radius less than 1, which means that in this particular state, as you can see, even the states converge. There is a stationary point over here, and so you can see clearly that the trajectory of our system stays in this region of lesser than 1 spectral radius, right? But in this uncontrolled region, even though you're not really applying the control, it's really still helping you understand regions where if you start applying your control, you may suddenly have like a growth of action norms, right? So this is quite convenient. Okay, let's go to another example where things become more interesting, right? So this is the cart pole example, right? Another very elementary example of RL for controlling a problem. The idea is to control this cart so that the pole remains upright. And we apply the same approach. We have a pre-trained model. We do the SALSA-RL type of post hoc training, and we employ it. You can see the magnitude of the actions is high initially, but then it basically drops down, and you can see it never goes to a flat line. In comparison with the with the pendulum, where you can see the magnitude of the actions basically flattens because it's able to basically, essentially solve the problem and keep the same action. You can think of this as trying to balance a pen on your hand. You never truly can keep your hand perfectly steady. You have to apply small corrective actions to keeping the pen upright. And this shows up in, firstly, if you do an analysis of the spectral radius and the eigenvalue of the state-dependent A matrix, you'll see that the imaginary eigenvalue is always non-zero, right? I mean, it's predominantly non-zero. So you know that your action is always going to keep oscillating over time steps. So there's no hope in getting sort of like a stationary type of behavior. The other thing that you'll notice is that the spectral radius is also, this is again locally computed, right? This is not that's why the spectral radius changes over time. It gets close to this region of stability, right? So anything below 1 is locally stable, it gets close, and then it kind of saturates right near the border, right? So if, for example, and Shuyang, we should probably look at this, if you are able to compute a moving average of this guy, right, we will find it to be very close to 1, but not less than 1. And that's because there is no steady state that exists in this problem. So it can't really go less than 1 permanently and then basically not change the actions at all. But one thing we noticed, again, this is the first time we noticed it, but we have more examples of this coming up, that in systems where there is no steady state, right, such as the carpool over here, you can't expect the spectral radius to be less than 1, but we do see that it essentially ends up in sort of like a type of convergence with slight oscillations near this boundary of stability, right? So this is something that we found very interesting. This also shows up in the contours that we talked about, right? So whenever we perform these analyses, we plot these contours. Anything within the white line is our so-called local stability area, and and we were able to see that again. So these plots are obtained by marginalizing across the other values of the state that our pre-trained model always brings the system to regions such that it's at the boundary of stability, right? It's never far away. And you can see over here that the imaginary values are always non-zero. That's because, again, the actions have to keep being tweaked. The nice thing over here is that we could, we could generate this contour without actually having the red line, right? And we could probably come up with a very nice guess as to how the red, the trajectory might look like without actually executing our agent, right? So that's another nice thing about this work. Okay, another example here, we'll look at how things behave when we are crashing, right? So we have two cases over here. We'll go over these cases one at a time, but this is a lunar lander benchmark. We changed the benchmark slightly to, instead of guiding the lander to safety, we wanted to keep hovering over the surface of the moon. And because hovering requires the actions to continuously be performed and not switched off, right, once the lander lands. And you can see that even though our agent is pre-trained, there are certain initializations of this lander which lead to a crash, basically, even though it is pre-trained to provide this. So this is an example that is very interesting for us because we want to see how exactly our analysis changes, or what the insights from our analysis are when we have a catastrophic failure, right? So okay, so let's see. So the first case is a good case, right? So in this case, our pre-trained agent, we do this this SALSA-RL analysis, and then we deploy it. We are able to essentially stabilize our lunar craft appropriately. It hovers properly, and it'll indefinitely hover. Of course, we don't consider things like fuel and stuff. And if you look at the action space over here, there is initial transients, but over time there is the horizontal action basically essentially flat lines. The vertical action keeps sort of flickering up and down. It's because the surface is not even. So as it gets close to this sort of mountain over here, the vertical action kind of starts acting up, because one of the things we actually observe is distance to the nearest surface. And if you actually make a plot of the spectral radius and eigenvalues over time, again, we see that there are non-zero eigenvalues for the imaginary component. This makes sense. There is a unsteadiness. There is an oscillation that happens in the actions, which can also show up over here. But when we plot the spectral radius, you can see that over here the spectral radius actually again stays near the neighborhood of the one sort of boundary, but over here it's basically below the one boundary and stays kind of close by. So again, it kind of matches our observations in the previous case. If we are to make a plot of the nature of the contours, again, this is the trajectory and state space of our lander across the state space is much higher. It's not two-dimensional, but this is like a marginalization over the other states. You can see that the nature of the landscape of the stability, local stability landscape, you can see the boundary remains relatively well placed. This is something again that we observed about the safe applications of these agents. The boundary in this area becomes essentially becomes kind of reliably located. So this is just a still frame depiction of the same thing. But in the second case, where we have essentially like catastrophic failure, right? It's the same agent. It's just that it was started with a state action combination, which is not quite right? So over here we started on the top left. So the location and the distance from the surface is different. And we also provided an initial action, which basically made it kind of unstable. It was going to crash, couldn't really stabilize over time. The first thing to notice is that the magnitude of the actions are very high. They don't kind of flatline to low oscillations, as you can imagine. The second thing to observe is that when we compute the spectral radius, it never really reaches the boundary. In fact, it tries to get close, but over time it gets further and further away from the boundary. So this is something that we see close again and again. Instead of interpreting the spectral radius to be something that is an absolute number, like interpreting its absolute value and then taking a decision about the goodness of your pre-trained agent, we want to look at its trends relative to the boundary of local stability. And so the trend in the previous case was basically to be, of course, persistently below 1, which means, okay, you're safe. But in the case of the, if I go back a little, in the case of the cart pole, you see you did have the value of rho to be higher than 1 occasionally, but you can see that that there was no trend to sort of go away from the boundary, right? So that's something that over here was associated with instability. Okay, a final example, which is the most complicated that we looked at, which is a bipedal walker. So over here, we have to train this object to basically walk over the surface. There's a very high dimensional state, so visualization becomes more difficult. So these matrices become, these metrics become more important. You can see over time, the state and actions, they are widely oscillating, even though the agent is trained and being deployed. And if you actually now plot again, the spectral radius and the imaginary value with respect to the one location, we are much further away from the boundary. But if you carefully pay attention to the trend is to stay the right distance away from the boundary. So this is what I was mentioning. If your spectral radius is basically relatively constant and the distance to the boundary is also relatively constant, then you're looking at an agent that is typically going to be stable and safe. But if you deploy this in a way such that the agent basically has a spectral radius that's going further and further away, it's rising away from the boundary, then you're looking at a possible unsafe behavior, right? So this is also contours that are demonstrating the same things. I'm going to keep moving. Some other things that we look at, which add a little more sort of insight into what happens if even if you are locally stable consistently, you can still have short-term transient growth due to non-normality, which is the A transpose is not equal to A transpose A. So there is this constant called the Kray's constant, which can be used to measure the potential short-term amplification of the system. And we can plot this constant again. We'll go back to the pendulum case, right? So the first case is the one which has a stationary state. So over here you can see there is some unsteadiness. So looking at the left column over here, the Kray's constant is you can see it's basically changing over time. So there's an unsteadiness in the Kray's constant, which also corresponds to the spectral radius. So that's good to see. But then after a while, as this pendulum is basically perfectly held upright, you basically have this constant becoming flat, as does the spectral radius, right? But in the second case, we have a modified environment for the pendulum, where we increase the acceleration due to gravity from 9.8 to 15. So in that case, and since the maximum torque that we can apply is actually is limited, our agent is basically never able to bring the the pendulum upright, so it keeps oscillating between extremes in the sense of the actions, so the torques, to try and on average keep the tip of the pendulum as upright as possible, right? So it's a case in which you haven't met your objective, but you have come up with a policy that somewhat maximizes what you can do. And you can see over here that the spectral radius, of course, is varying over time. But you'll notice again in this particular case, it's almost like a system which cannot fail, right? So that's why if you were to plot the average expected value of this spectral radius, it would still be flat, right? So it's still safe behavior in the sense of how we are defining it. The Kray's constant, on the other hand, you can see it also tracks this instability quite nicely, definitely in comparison to the imaginary value of imaginary magnitudes of the eigenvalues. So you're able to get a little more detail for the oscillatory nature of the action norm growth, right? Okay. Finally, we have how much time? We have 8 minutes, so I can quickly go over this. So in many systems, such as, for example, this one on the bottom, you can sort of set up a description where there is a periodic behavior of A, right? So in some sense, in this previous example, we were looking at states that were recurring after a fixed amount of time, and so this A would also recur after a fixed amount of time. And so we can perform some Floquet analysis to actually then analyze whether the long-term application of this periodic matrix is actually going to lead to stable decay of these actions, or is it going to lead to exponential growth, and so on. So it's just another type of analysis that we can do on top of the spectral radius. But it leads to an interesting insight. So let's apply this to these two cases, these two pendulum cases. And so in this first case, when we apply the Floquet analysis, we actually get values of 0. This is another confirmation of the framework, which says that if the value of mu is 0, it means that you basically have no growth, no oscillation. It's basically stable, right? But in the second case, which is the case where with the high gravity, we actually gave Floquet eigenvalues, or Floquet multipliers as they're called, which correspond to instability. And this makes complete sense, because in this particular, so what does instability mean over here? This means that if we apply our periodic system on an initial condition for the actions and evolve it indefinitely, the actions will basically explode. So basically, what this is telling us is that to solve this particular problem, as the agent has been pre-trained, it'll keep applying larger and larger torques to get close to the top, and thereby hit our clip value. So in both these examples, the actions, the torques are clipped because they are clipped, because you essentially that's the maximum capacity perhaps of the actuator, right? In this particular example, if we actually remove the clip, you will see that the deployed agent will actually become unstable over time, right? So because of the nature of this behavior. So this is kind of like a roundabout way to justify why clipping is needed for the second case. Because it counteracts the behavior of these of this periodic system. Okay, just a note that I want to leave with at the end of this talk. We spoke a lot about how we were able to interpret things from the deployment of this task, but we didn't really talk a lot about the final score. So how did the rewards look like when we compared across these different methods? Well, what we didn't want to do is outperform the baseline trained model, right? So we didn't want to propose a new reinforcement learning algorithm. And our statistical tests actually prove the same thing. So even though these are trained using DDPG, we essentially are able to recover the same behavior in the sense of the expected reward when we actually deploy this on a new test data, right? So we are able to basically perform about the same. One thing to note is that the latent space does play a role in the performance of this reinforcement learning algorithm, which I guess if anybody has fit autoencoders for dynamical systems, they would concur that the dimensionality of the latent space is important for having an expressive representation of the actions. And so too lower dimension, and you're looking at for complicated systems like the bipedal walker, you're looking at basically poorer performance, right? So this is something that that must be mentioned. Okay, all right. So I'm going to basically conclude over here, saying that this work is under review. It's on the archive. Feel free to look it up and reach out to Xiang or me for questions. What we're doing over here is we're essentially, using very elementary methods in stability analysis of linear dynamical systems into a pre-trained reinforcement learning agent by just identifying a latent space where this linear dynamical system can be implemented. We look at various methods to actually look at the state-dependent matrix A and tell us something about the behavior of our agent in combinations of state and action space, right? Because now once we have this pre-trained matrix A, we can give it combinations of states and actions to actually see how the action of that matrix changes a particular action. So it's how the influence of that matrix changes a particular action. But more importantly, this is just a very easy sort of addition that you can make to all your reinforcement learning workflows that is pretty easy to train. We didn't use any high performance computing for this, just a simple application of GPUs. It was quite straightforward to maintain the performance of the original pre-trained agent, but at the same time, it gave us some insight into how the agent may behave in an unseen environment, right? In an unseen sort of situation. So, okay, with that, I'll stop over here, and I'll just like to go back to the title slide and mention Xiang, who basically, led the development of this work and is really the brains behind it. So thanks again, Shuang, and if you guys have any questions, or if you want to use this, or if you have feedback, criticisms, if you're angry, feel free to reach out to the both of us, and we'll be happy to have a conversation. Right. Okay, so I'll stop over there. Thanks, Sahil, again for the invitation.
Thanks. That was a really, really nice talk. Thank you so much.
Sure.
Yeah, with that, we can open the floor to any questions, over your question.
I had a quick question. So, for the pre-trained model that you take in order to then do this stability analysis, does the policy being deterministic or stochastic change how you sample let's say, the actions in order to train the autoencoder, or does it have any sort of impact on how you interpret the latent space?
So conceptually, no, it doesn't have. I mean, we treated, we treated it in a unified manner. But empirically, I mean, in this particular work, we looked at only deterministic policies. But my understanding is that it should be about the same, right? We don't see that to be, because in some sense we are it actually, the stochastic policy actually fits better with our setup because our matrix is state dependent, right? And the policy is also state dependent in the sense of the distribution of stochastic policy typically has a variational sort of formulation, right? It's conditioned on the state. So so in that sense, I think it's if we had a time independent matrix or a state independent matrix, say, then the stochastic policy would give us a headache, right? So but over here we kind of bypass that. So
and then one more quick follow-up is, so in that lunar lander case, for the second case where you showed that it is unstable, was it just a different initialization of the lander, or was something else also changed in that environment with
So
respect?
my understanding, it was a different initialization, so different initial action, different initial state. But Xiang, is there anything else I'm missing for the second case?
I missed the question part. Can you use?
So I was just asking if anything changed between the environments in the two cases, or is it the same terrain?
Yeah, the initial condition, mostly the initial condition. There's just a reset by manually, mostly just initial condition. Yeah.
So there's no change in the environment. I think maybe the surface is changed, but
Yeah, the surface, yes, yeah.
Understood.
Yeah.
Yeah, I had a question about case 2 in this case. So you did mention that you specifically select an action and a state value where the rover is going to crash. So was that decision informed by the analysis, or was that just empirically found, okay, this is the case?
You can do it both ways, but I think what we did over here was we basically just randomly initialized it in different cases and found a case that crashed.
Okay.
Yeah, so so in that sense, you could, for example, compute the initialization such that this initial spectral radius is very high, right? It still doesn't guarantee that it's going to be a crash, because if you look at the bipedal case, right? So the spectral radii are high over here, but the chances of this being unsafe are probably higher. So I don't want to say that we can just use a single sort of metric to determine if something is unstable or not. But what we are interested in is basically the fact that the spectral radius is actually how its trend changes over time, right? So that's actually been the most revealing thing over here, right? So you can even notice it in this plot over, maybe this plot over here, right? So the initial condition here, you can see it's on the left side of this boundary. So the spectral radius is high, right? So it's high. The initial action of the agent actually tries to brings the lander close to the boundary of sort of local stability, but over time you will see that the boundary just moves away, right? So the distance from the value of 1 is something that we are finding to be very important for these actions. So you can see this over here as well, right? Over time, this distance from this boundary just grows, it just runs away. And that's kind of also characteristic of maybe the fact that you're out of luck, right? No matter what action you take next, you're going to be, it's just going to get worse.
I see. Do you think in using such analysis, you can enforce some risk sensitive or risk averse action taking?
Yeah. That's a good question. I mean, we haven't really thought about that in a very rigorous sense, but certainly there is a extension of this, I mean, that we can identify where we can do some planning, right? So the idea is that this trajectory is now under the influence of a pre-trained agent, correct? So, but we can, in some sense, generate these contours like without having to actually interact with the state, because um, uh, you can basically, I mean, it's going to be very challenging in some sense because it's going to be a high dimensional state, and a high dimensional action. But you could compute the spectral radii. So the end goal is this guy, right? So we can maybe here, right? We can provide the states for a particular action. So the action can be encoded to a Z. We can provide a state that will get the A. We can then analyze the action of Z, action of this matrix on this state. We can compute the next state in this latent space, but we don't have to apply the state into the actual environment. You see, now we don't have to like sorry, let me take that back. We have to provide the actions and provide the state at a particular location and see how the actions change, right? So now our state space is the universe we are working in. So our state space is hopefully bounded. It has to be. So we can provide different state spaces. We can provide different actions, and we can actually assess how the stability properties vary across state action combination. Does that make sense, Sahil?
But then, like at each time step, how can you like limit your action space? Like there's already a pre-trained model,
Yes.
right? In this case, so you already have like what's the distribution of actions given whatever the state is. But now, if you want to add like outer loop to it, where you're like, okay, based on my stability analysis,
Yes.
at any given time, I wanna, based on some risk measure, I'm gonna limit the search of the actions, or like want to make sure that at least the agent's locally stable in some sense. Now it doesn't guarantee like the overall stability of the system, but like for example in the chaotic
So
system,
yeah, I understand, Sahil. So I guess the answer to that is, instead of having, you can have like a dynamic clipping now, right? So typically people use clipping based on preset values of the maximum and minimum actions, right? Let's say now you could potentially have a stability informed clipping, right? So you clip when you need to clip, right? Because you feel that you're getting into an unsafe behavior, right? So that could be something that we could, but I haven't thought about this too deeply, so I'll have to sort of get back to you on that, right? So
it's very interesting. Thanks so much.
Yeah.